I already said before, these constants are not true constants, they are running constants. They change somewhat when you go to higher energies. And that is an effect of renormalization. Renormalization really means that you have to somehow define these constants, not to be fundamental constants in my equations, but fundamental constants in the outcome of your calculations. So you use the equations, you calculate something, out comes an amplitude, a property of particles that you will check with experiments. Those properties are described as finite numbers. You put those finite numbers in, and you ask how are they related to the numbers you put in the equations. And those relations contain infinities. But it just means that in the formal equations, there are quantities which, bureaucratically speaking, should be infinite, but we say only finite components of these interaction strengths actually matter. They describe the particles direct, and the infinities themselves are hidden in the procedure to your calculations. Now this sounds fuzzy, and deliberately I give you a rather fuzzy definition of what renormalization is. We can say things a lot better, but you have to pay a price for it. One is that you have to do perturbation interaction. Really, it's not defined completely accurately by the equations. What you have to do is you have to solve the equations stepwise. You first do the rough calculation. Then you say, I'm going to do the refinement due to corrections in the equation. The equations are not solved correctly. I take the next correction. They have to write the next correction, and so on and so on. That's called perturbation expansion. The interactions are considered as perturbations. You first assume the perturbations to be small. Then you discover the perturbations are being perturbed again. You repeat the calculation to the next step, and so on and so forth. This is called perturbation theory. In perturbation theory, you can compute what happens to these interaction parameters stepwise. Every step in the perturbation, you have to redefine what these parameters really mean. They are shrouded by infinities all over the place, but you have to understand what that means mathematically. You have to give rigorous definitions of these parameters. We are completely under control of the situation, provided that we limit ourselves to spin 1, spin 1/2, and spin 0. If we add spin 2 or spin 3/2, then we know these series are not renormalizable. Renormalization doesn't work. And there are many physicists who say, well, we've learned to ignore such problems, so we don't ignore them here as well. And you can get a long way doing that, but eventually that's unsatisfactory. We have to be more precise in formulating things. And be very much involved in this whole procedure. I know how important it is to understand what you're doing. And when you try to renormalize gravity, I'm somewhat disturbed by the fact that people often do not understand what they are doing. We should. So we have to try to understand more precisely what renormalization means, and not be content too quickly by saying, well, it has been solved in the past, this will be solved in the future, we don't care, we just continue. And it's a little bit disturbing, and I find it disturbing also when people do supergravity and string theory, and very often the notion of renormalization is sort of considered as a problem that will sort itself out someday. And it's not that easy at all. And in fact, this generates difficulties. So this sector of the theory, in particular when h bar is unequal to 0, this sector becomes fuzzy and unsatisfactory to my taste. Even if you put in the most modern theories, in particular string theory, but there are also other approaches that people try to address this problem, because my colleagues are not stupid at all. They know very well what they're doing, so they realize very well this difficulty. They try to get their formalisms as accurate as possible. And I don't contend with today's result in general. They should be made more accurate. So to make the theories more accurate, you need new principles. So I will now start to address some principles which I think you have to introduce to make the theory work completely. Now, so this is the situation that we have in physics and that I want to address. How do you start addressing this apparent difficulty. And again, I haven't been writing many equations on the method yet, and I won't do that today. We'll get to equations soon enough. But the question is, how do you, what would you do to try to improve our understanding by being smart? Well, we've seen how it went in history. We've seen how all this beautiful piece of knowledge came about. People are asking questions, and the more accurate the questions are, and the more accurate the answers are, the more progress we are making. So we want our theories to be very accurately formulated. Now, the domain of physics where this really becomes fuzzy and unsatisfactory, at least to my taste, is when you look at black holes. Now, already in Einstein's time, Einstein wrote his theory at the end of 1915. Already early 1916, there was an astronomer named Schwarzschild, Karl Schwarzschild. He was a well-known astronomer in his time, and he saw Einstein's equations. And he saw that Einstein had made a perturbative solution of these equations. So he wrote down the equations for the radial motion of Mercury. Here's the sun, and Mercury goes in an ellipse. Mercury goes around in its ellipse around the sun. Einstein used perturbation theory. But Schwarzschild said, hey, wait a minute. In this case, that h bar goes to 0, I can write down exact solutions to your equations. Why do perturbation theory if you can do it exactly? So Schwarzschild wrote down the exact solution of Einstein's equation. And noticed something that you could say Einstein had missed. He said if you have a sun and a planet going around it, everything is fine, but there is a region around the sun. Well, there are lots of details here to be mentioned, but there's a region around the sun such that if a planet would come close to that region, it would sooner or later reach the speed of light. You can calculate that, and indeed the external observer sitting far away, could measure the velocity of the particle, and the velocity of the particle would increase and increase as it approaches the center. But there will be a point where it will follow the speed of light. And now you can use, what happens next, you can use fuzzy words to describe it, and then all the crackpots come to you saying that that's not right, and you know how to do it better. They don't know how to do it better. Mathematicians know how to describe this very, very precisely, what happens to a planet when it comes too close to the origin. There's a region called the horizon, where you could say the velocity of the planet reaches the speed of light. But that statement is not quite accurate because you have to say who is observing and what are the notions of length and time you're using. Because all that is subject to dependence on the observer if you read Einstein's theory carefully. So saying the planet reaches the speed of light is an observer-dependent statement. But you can say very precisely what happens. Space and time are curved, and there's a region here where the curvature is such that if something goes inside, it will get faster at the speed of light. And it would imply that the thing cannot come back. So once an object is here, it will go to the origin rate of time itself. Now the equations are looking pretty strange when you reach this point. So strange that Schwarzschild said, I'm free to choose my coordinates as Einstein told me. Remember, the theory was only a few months old. So Schwarzschild had not totally understood the situation, but he understood you can make a transformation. So he said, I call my distance my radial coordinate r, I'll go to another coordinate r, and basically I just say that capital R is big R plus 2gm. This is not precisely what Schwarzschild did. Schwarzschild had a very good way of making this transformation, which roughly looks like this actually. a bit more complicated, but that's immaterial. Basically, what Schwarzer did was he redefined R such that this entire circle here is on. I'm saying it right now. Yes, I should put here. Yes. So this R is 2GM. The little r is at 0. So we just push the origin of space-time on this circle. And you can get away with that because Einstein allows you to make coordinate transformations. And then he said, I just removed my problem because I put it all at the origin. At the origin, everything is singular, and that's because I'm assuming a point mass. Of course, point masses don't really exist in nature, so therefore, what happens at the origin is somewhat fuzzy. I don't really understand that region, but now the problem seems to be removed. Some people think that's the way to remove the problem, but that's not correct. This doesn't remove the problem at all. It is much better to keep the original coordinates, which Schwarzer would call capital R. Usually now in modern physics this is called little r, and we never use that one. So in practice we never put this whole circle, actually it's a sphere of course, we never put that sphere on the origin of space-time. That would be impractical. It's much better to keep it where it is and to ask the question what happens if something goes through that sphere. And what happens is you go through the horizon of a black hole. And, well, we have lots of features of black holes. Nowadays, 100 years later, people have gone over the equations thousands, millions of times, and now we know very precisely how to compute things near a black hole. But again, we know how to compute things if you put h bar equal to 0. But what happens to a black hole when you switch on quantum mechanics? That turns out to be an extremely interesting question. A question where indeed people get confused. What is a quantum black hole? And the nice thing about this question is that if you try to answer it, you discover that if you follow the books, if you follow this theory or that theory, in all cases you get answers which can't be right. And that is very important. That means that we are missing out on something in physics. And that situation is very reminiscent of the situation that drove Max Planck in 1900 to rephrase the laws of radiation of heat. Max Planck realized there's a problem in statistical physics with Maxwell's theory. Maxwell's theory of statistics, what is the statistics of Maxwell's fields? He gets into answers which can't be right physically. A problem with that which looks like the problem that we have today. Now Max Planck was a genius and he found the answer to the problem. He found that energy must be quantized. And that was the beginning of quantum mechanics. So that was the correct answer in his day to a very, was it, paradox. Now with black holes we guarantee a paradox. Now when you read things that string theorists write down, they say we solved the paradox more than one. I think the paradox is still there because the understanding in string theory is less than perfect. They have a rough way of calculating things where all the difficulties disappear. String theory is supposed to be finite, it's supposed to be free of renormalization problems. And this paradox at first sight looks like a renormalization problem. But it's more than that. And I claim the paradox has been, they talked it away. A little bit like Schwarzschild talked his horizon away and putting it to origin, so it's not there. The paradox, I think, is still there. And we should try to address it in a better way, in a more complete way, to unify black holes with the rest of physics. Black holes are a necessary consequence of general relativity, so you can't talk them away. Even though, strictly speaking, the only occur on h bar is 0. You could argue, and I will argue, hopefully I'll reach the point tomorrow, why at h bar not equal to 0 there are no black holes. But I have to say what I mean with that. And you can't just say they are not there. That's not the way to solve questions. They are there, they seem to be legitimate solutions of the equations. But we have to get the grand total of physics So if there's a region of physics where things seem to go wrong, we have to see, is there something wrong with our understanding of the laws of physics? That's what Planck did at the time, and I think that was a totally correct way to react. There's something that we don't understand in laws of physics. Let's try to address the problem as accurately as we can, see how could the laws of physics that we know be modified, of course without jeopardizing all the successes of the past, but doing it in such a way that now my problem is solved, and now we understand how these objects behave. So in the case of Max Planck, but now we understand how to do statistics with radiation, and in the process of getting that understanding, we are making improvements in understanding laws of nature. That's the way the area I want to investigate in these lectures. How can we improve the laws of nature as we know them, improve our understanding of the laws of nature, such that black holes are described correctly. And I will show, and I hope in the end of the lecture I will show, that even this problem of these fundamental constants may very well be related to that. These constants can be arbitrary real numbers, but they're not arbitrary. They should be calculable. Are they calculable? Well, if we manage to improve laws of nature, or to improve our formulation of laws of nature, such that black holes behave in a decent manner, you might get as a recognition, now we can compute these numbers. It isn't like that, of course. If that were true, we would have known more in advance. I'm going to show you a spectacular way to compute these numbers. I cannot show you that. So, of course, I cannot do that, but I can show you that there should be ways to address these questions by asking nasty questions here. And by not being content with half answers. I think the answers that you have today are only half answers. The answer, yes, you can compute black holes such that they behave decently. But no, they're not quite the black holes we're interested in, that you have previous computation for. And no, we don't really quite understand the mechanism by which these apparent contradictions go away. But I haven't yet told you what the contradictions are. I think it may be a good point to have a short break here, and then I'll go into more detail about this black hole physics and what actually the problem is at the point of this break.
Perhaps we can take a few questions on the past, if there are questions. No, I think okay, I have one question. Because you said that going at the speed of light depends on the observer. That should be dependent on the reference frame.
Of course. So I said it in a very rough manner. This can be stated much more precisely what this means. And there's a way of saying that whenever something falls become too close to the origin of structured solution, then in a certain sense you reach a speed of light. But what a certain sense exactly is can be phrased much more precisely. Actually, it turns out this is a domain where the structure space and time is such that you can move in, but you can't move out. And the fact that you reach a speed of light is only correct if you use certain terminology that I don't want to be dependent on. So you're quite right to say this is an objective way of saying things. It's just a way of categorizing, in a very rough way what is happening.
Actually, I have another question. At the beginning you started mentioning unified theory.
Yes.
Now this is a matter of perception, but you think that there is a larger group, that there is a unification, say, the old style, I mean, that one single gauge group with another X mechanism and a large number of vector bosons and then proto-decay bits.
Well, actually, what I said here, I was just copying what many of my friends said in the 1970s, 1980s, and quite quickly reached. I mean, it's not so difficult to say that SU3 equals SU2 equals U1 may well be a subgroup of SU5. It works very nicely. And SU5 is a subgroup of SO10. If you look at SO10, all these matter particles form one spinoidal representation of SO13.1. So this is very suggestive. It looks as if nature's trying to tell us something here. That SO31, which is space-time together with the internal symmetry group, looks like the symmetry group of which the spinorial particles are in one single spinor representation. It looks too good to be accidental, but that's about all I can say about it. Because up till today, we haven't seen very strong evidence for SO13, even SO10 here. We haven't seen very good evidence for that, apart from a couple of coincidences of this sort. So there's a certain number of coincidences saying that this looks neat. Maybe nature's trying to tell us something here. But reality could be different. And I'm very much aware of the fact that the true explanation of why these constants have their values could be very different. Actually, you may well know that SO10 gives you a relation between G3, G2, and G1, which is interesting because it tells you that these constants, since they are running in dependent energy, there's an energy domain where they are all three equal. That's an energy domain close to where black holes start to form, and in that domain it looks like SO10 might be the relevant group. So there are indirect indications that there are some number of coincidences. Nature is trying to tell us perhaps this is the way to look. But it's not more than coincidences, only a couple of numbers which seem to be reasonable. And so to be precise, we have these three running coupling constants. And if you take the inverse of the running constant, 1 over G1, 1 over G2, and 1 over G3, then these three numbers seem to, this is the logarithm of the energy. Here they are being extremely high, and this is where black holes start to come. These constants come very close together. They don't go quite close to 1 line unless you add supersymmetry. And this is has been argued in favor of supersymmetry. If you add certain particles, you have to make the whole thing supersymmetric. Spin 3 half cappuccinos and so on. Then it looks as if these particles, these lines go through one point. Well, at that point, it's fairly close to a domain where black holes start being important. So, perhaps, this could be a coincidence. You know, 3 lines go through 1 point, not very precisely, but as accurate as you can compute them. So, what does it mean? Well, you could certainly think nature's trying to give us a message here. Let's take it seriously. Let's take it seriously, but we don't know for sure.
Okay, the ice has been broken. One last question and then we'll go for the...
Yes, I profit of the audience and the fact that you are Dutch, just to mention Johannes Droster.
Sorry?
Johannes Droster,
Yes.
who was Dutch and a student of Lorentz, and who discovered 4 months later Schwarzschild in the same, well, almost the same solution. Actually, what we call now Schwarzschild solution is the Johannes Droster solution.
Yeah, Schwarzschild made this transformation of the arc ordinate, which is not necessary. But he didn't quite understand. He wanted to get rid of the strange difficulty at the origin. But that's not the way we should handle a problem, like transforming it away. You can do it, but that's not right. And also, I think, did not do that. So, but in those very early days, it wasn't quite understood. This was a horizon. Now we understand that.
Okay, thank you. We have coffee and